Good evening, ladies and gentlemen, boys and girls, and welcome to the Hertford Astronomy Group. Whether you're a newcomer to our group or a regular visitor, we are pleased to see you. Permit me to introduce myself. I am Alan Willison, and I am the chairman of the Hertford Astronomy Group. We begin this evening with a little bit of sad news. I'm sorry to report the loss of Simon Pearson to our group due to COVID. Simon really enjoyed coming along to our group, and our thoughts go very much to the Pearson family. This evening, we are going to hear about the forthcoming items of interest in the night sky from Martin Weston. Following that, Jerry Stone will introduce each of our guest speakers for this evening. We're doing something unique for our club tonight in that we have 4 guest speakers, all from the University of Hertfordshire. You'll be able to ask questions via the chat facility, and Jerry will explain that as the evening progresses. Following the talks, I will be closing the meeting after giving you insight into next month's meeting. Tonight's meeting is being recorded with the permission of our speakers and will be made available on YouTube by Saturday. A link to the recording will be posted on our website when it is ready. Links to previous meetings can also be found there. As a courtesy to our speakers and fellow guests, we ask that you keep your microphones muted. So it is with great pleasure I pass you to Martin.
Good evening, everybody. I'm going to attempt to talk about what we can see in the sky. Although it's not been very good just the last few months, I'm sure that we've all been a bit disappointed by the visibility or lack of it. Okay, everybody, I hope you can see the screen. Can everybody see the screen okay? Good. Okay, so I normally sort of flash quite a few images up when I'm doing my talk about various objects in the sky. And I was just contemplating the other day that people might, I'll go and find that. And they look in their binoculars and they look and they say, I can't see that. I can see nothing like that. So what I've tried to do tonight, I've got some images to try and show you what you're likely to see through an ordinary pair of binoculars or through a small telescope. So this first image is one I took a couple of weeks ago of the Crab Nebula, as it looks, but that's with quite a few hours of imaging to produce that image. I'll just quickly show you where that is. So hopefully you'll be able to see that. I've zoomed in a little bit, but we're looking sort of south, and this is the Orion constellation here. You can see Betelgeuse and Bellatrix here. So if we come up slightly, we've got the Seven Sisters. Most people know where that is or see that in the sky. It's a good reference point to find things. If you come down from the Seven Sisters, there's this quite yet orangey bright star, Aldebaran, is in the Hades cluster. So if we follow that star along, so we can see these stars here in a bit of a zigzag, but they're almost in a straight line. If you follow it across to this star here, it's Tihangian, and the M1 or Messiers 1, the Crab Nebula, is right next to it there. So what I've done is taken an image of what you'll probably see. So it should help to hopefully find the object, but to have an idea of what you're looking for. So there's the star we were looking at, Tihangian, and there is the Crab Nebula. It just appears as a little fuzzy blob. But it's still good to look for these things and try and find them, because there's nothing like looking at the actual object with your own eyes sometimes, just so you've seen them. The second object I picked on is the Orion Nebula. There's another image I took. I haven't imaged this for a couple of years now, so this is an old picture, not the best one I've ever done. But just to give you an idea where that one is, and it's certainly worth having a look for. If you've got good eyes on a really good clear night, you might even be able to see it with the naked eye, but I would recommend looking for a pair of binoculars or a small telescope. So here we are, this is the Orion Nebula, Orion constellation here. So we've got Betelgeuse and Bellatrix, Rigel and Seth there. And then we've got his belt here. And then coming down from the belt, we've got his sword. Now, if you follow the sword down, it appears to have 3 stars in the sword, but that middle star there is actually the nebula, is Orion Nebula. So you'll probably see it like something like that through binoculars. But again, just with a camera on a tripod, you could get a color, you get a bit more color in that. It's just, you need to remember that our eyes on long distance not pick out colors the same way as a camera can. So a lot of these things do appear quite bland, but it's still great to find these things and see them. I remember the first time I found the nebula just through a pair of binoculars. It was great, really, just to find these things for yourself, not just see images that someone else has taken. Another fairly bright object that you can find is M31 Andromeda Nebula. Again, this is a really old image. What I just noticed is actually a satellite traveling through the center of that image. So just quickly put these together. It'd be lovely if you could see it like that, and in a couple of billion years we will, because we're actually getting closer to the Andromeda Galaxy. So it will fill the night sky eventually, not in my lifetime though. So just to find Andromeda, we're looking another part of the sky. We're sort of looking northwest here, but most people recognize this particular constellation, Cassiope. It's the W in the sky. So if you look at the 2 bottom stars here, this one here on the right hand side or below on the bottom, this particular way this is imaged, is Shedna. And if you follow it across here, there's another bright star here, Myrak. And if you come up 2 stars to there, and then slightly off to the right, that is where the Andromeda Galaxy is. And if you took a picture of that, it probably looks something like that. Or if your eyes can see it in a really dark sky area, it appears just again as a fuzzy blob. This is quite a large, well, it looks small in this image. Its full width, length from there to there is 3 or 4 moons. You could get 3 or 4 moons in there in that size. So it's a large object. And if you ever try doing just putting a camera on a tripod and doing a long exposure in your garden, pointing at the Milky Way, you can usually find this in there because it appears quite readily. So that's the 3 main targets I've picked that are really quite good to see at this time of year. So we'll just have a look at some other bits and pieces that are going on. So we've got a new moon tomorrow. We won't see it, unfortunately, for a day or 2 because the moon's actually in between us and the sun. So, and it's like the sun is actually lighting up the far side, so we can't see anything. But within a couple of days, we should start seeing a thin crescent moon coming up. So it will appear in the western sky in a couple of days. So. Another interesting object that might be worth a look is Algol, the star Algol. And it's one of the most accessible variable stars for sky watchers. And a variable star is a star that becomes brighter and duller over a period of time. And this has got a sequence. So for 10 hours, every 2 days and 20 hours and 49 minutes, the brightness dims. And the reason for this is it's actually a binary star, and the other star, the companion to Algar, is actually dimmer than Algar itself. So when it actually eclipses the front of Algar, it actually reduces the brightness of the star. So we go from 2.1, which is quite bright, down to 3.4, which is identical to a star which is about 2 fingers away, Roa per se. So yeah, see if you. I'll show you where that is in a minute, but that's certainly on Friday. If we've got another clear sky, it's certainly worth looking at that. So again, we're in Cassiope over here again, where we were looking, where Andromeda was over here. But this time we're going to follow my up to the top here, and you've got another star up here, Murphak. And if you come down, Algol's here, and you've got the Triangulum here as well, which is another constellation. So that is the star, and it's quite easy to find. So I would recommend having a look at that. Another, we did look earlier on, I did point out to you, Seven Sisters is finding something in the sky, but they are brilliant at the moment. They're almost overhead. And I'd say with a naked eye, you can usually pick out 6 of the stars in that particular cluster. These are very young stars, very bright, hot white stars. But through a pair of binoculars, there's so many more stars to see, or even, you know, a small telescope. It's a spectacular thing. This image here is showing the main stars in the constellation, but it's also showing this blue mist that appears around the stars. That actually is a misconception, because this is closer to us than the stars. The stars are actually lighting up this nebulosity around this constellation. So, but yeah, that's quite a spectacular thing to image again as well. If you can bring these blues out, then you know you're getting some good image, a good image. But yeah, definitely an interesting constellation to have a look at. So going back to Orion there, so I did point this out to you earlier on, but there we are. It's sometimes called the small plough because it looks in the same shape as the plough, and it's in Taurus, the edge here, on the edge of Taurus, and there's Orion Nebula, the Orion constellation there. So another easy one to find, but very, very high in the sky at the moment, so it's really good to look at. Going on, Sirius, we don't see it all year, but it is the brightest star in the night sky. So it's certainly a beautiful star to have a look at. And at this time of year, it gets us virtually as high as it's going to get. It doesn't get much higher than it is at the moment. And Sirius always, because it's very bright, always appears to twinkle quite a bit. And the reason for that is because it's low in our atmosphere. It's the distortions of the atmosphere that cause it to appear to twinkle. It's actually the light refracting on the atmosphere as it comes through. But it's actually, again, this is a binary system. It's Sirius A and Sirius B. So that is something quite beautiful to look at. I would recommend. There's quite a few nebulas around that I've been imaging around there, so I use that as a guide. Nebula I showed last month when we were looking, which was the Thor's helmet, which is quite close, and also I believe the Jellyfish Nebula is quite close to this as well. So it's a good reference point for astrophotographers. Okay, so we move on to the 17th next week, next Wednesday, if we've still got another clear night. We've got a crescent moon here, but it's a good locator for finding Uranus because it's going to appear roughly in between these two main stars, Menkar, Methium. And you can see this with the naked eye if you know where to look. But if you look through a pair of binoculars, you can actually see the color, sort of a greeny blue, turquoisey color planet. So it's obviously tiny because it's so far away, but once you find it once, it's something really worth searching out for. So if you get a chance to do that next Wednesday and we get a clear night, I would recommend doing that. Moving on, Saturday the 20th, we've got the pole-to-pole terminator boundary that divides the light and dark sides of the moon will reveal Rupus recta, I believe that's the correct pronunciation, for the lunar straight wall, which is this section here. When we get the moon at this position, the shadow throws up so much detail, these craters and so forth. If you can look at the moon in this phase with a pair of binoculars or a telescope, it's fantastic, the detail you can pick out. So that's something, again, if we've got a clear night, definitely go and have a look. And then on the 27th, almost the end of the month, we get a full moon. This is also known as a snow moon or a hunger moon. Don't know why. Should have researched it possibly. So when it's in this opposite to the sun, any of the surface discoloration on the moon is due to the variation in its albedo. And albedo is, the amount a planet reflects light from the sun. So we can see these dark patches, and the light patches are caused by the lunar terrain themselves and the moon's geology. So it's quite interesting that there's such a variance of colour, of shading, but it can appear as colour, depends on who's imaging it and what colour filters they're using. So that brings me to the end of my presentation. I don't know if there's any questions anybody wants to ask. I don't see any hands up, so I'll pass it back over to you, Alan.
Okay, thank you very much indeed, Martin. Some lovely things to be looking at in the sky out there when we get those opportunities to actually see it, and when we are wrapped up enough to be able to stay out there for a bit of time as well. But thank you for giving us a guide. I've certainly made a note there, February the 17th, to look for Uranus and see if I can manage it with a pair of binoculars. So thank you again. That brings us to the main part of our evening, where we are doing something that's a little bit unusual. Instead of having one speaker, we've been lucky that we've got 4 speakers, all from the University of Hertfordshire. So I'm going to pass you over to Jerry, who's going to introduce them one by one. So over to you, Jerry.
Thanks very much, Alan. Yes, we have 4 people from the University of Hertfordshire Observatory at Bayfordbury. We have had close ties with Bayfordbury for some time, helping out at their open evenings. And it struck me it would be nice to find out what the staff and students are investigating over there. And I'm very pleased to say that 4 people have accepted our invitation. And I was thinking earlier that this is sort of rather like Mastermind tonight. We have 4 participants, and their specialist subjects are using radio astronomy to investigate black holes, interpreting a mega collection of photos of the night sky, investigating star formation in the infrared, and that elusive property, dark matter. Now we're going to start off with someone who may have to leave before too long. So we're going to take her questions after her presentation. And if you want to ask a question, go down to the bottom of your screen and use the chat facility. So you can post those and we'll go through those. With the other 3 speakers, again, you post your questions and we'll get all 3 of them together as a panel and go through all their questions at the end of the session. So we start off with Jo Ramasawmy, who is a PhD student, and her subject is radio astronomy. She says that when astronomers began examining the universe in radio waves, they made a huge discovery that they could learn about all kinds of physics by looking at light outside of the visible spectrum. So she's going to talk about how we can use this invisible light to investigate what's going on in distant galaxies, and how Jo is herself using different kinds of light, from radio waves to X-rays, to try and understand how supermassive black holes shape the galaxies that they live in. So over to you, Jo.
Thank you, Jerry. I'll just set up my screen and we'll see if this works. There we go. Can everybody see and hear me okay? I'm going to stand up to try and, there we go, brilliant. Okay, so thank you so much. Thank you everyone from the Hertford Astronomy Group for having me here today. And I'm going to talk about what I've deemed invisible light, which what I mean by that is the light that we can't see with our eyes. So technically, the title of my thesis is a multi-wavelength study of star formation and nuclear activity in sub-millimeter galaxies. But I'll break that down in terms of the multi-wavelength part of it, using different wavelengths of light outside of the visible spectrum to explore physics in the distant universe. So let's get started. So I'll start by defining what I mean by visible light. So visible light, the light we can see with our eyes. And we might be familiar with the spectrum of colors that, that white light is made up of. So we have a spectrum of visible light from the very longest wavelengths in the red colors, all the way up to the shortest wavelengths in the violet. So the wavelength of light corresponds to the color and corresponds to the energy that light carries. So long wavelength red light is very low energy. And as we get through to the blue and the violet, we go to shorter wavelengths and higher energies. And this is just in the visible light. So a lot of the images that Martin showed us earlier would have been made by combining different colors of visible light, or perhaps just outside of the visible spectrum, images taken with a telescope. And when you combine those different energies and those different colors of light, you can build up a color picture. But as Jerry said in the introduction, it was only in really the 1950s that astronomers began to exploit using light outside of the visible spectrum to learn about the physics. Can everybody see the presentation, or got a message saying that it's not visible for everybody? Okay, good. Some people can see it. Excellent. Okay, I hope that if you can't see it, it appears shortly. Fingers crossed. Okay, good. Let me move this to one side. So as we move outside of the visible spectrum, we can see that visible portion of electromagnetic radiation that we call light is only a very, very small part of the full electromagnetic spectrum. So that goes from low energies, pointing in the direction, low energies all the way from the radio in the very longest wavelength of light, through the infrared, the optical, up to ultraviolet, to X-ray, and to the very highest energies, gamma rays. And these different wavelengths of light probe different parts of an energy spectrum of processes going on in the universe. So we can use the very longest, lowest energy wavelengths to explore very low energy processes. And we can use the higher energy, shorter wavelengths of light to explore very, very high energy processes. And that way we can build up a much fuller picture of the physics of what's going on than if we were to just use the visible light that we can see with our eyes. So there are a range of telescopes that have been developed in order to image the sky in these different wavelengths, all the way from the radio to the gamma ray. Some of those wavelengths we can observe from the ground. So we're probably more familiar with the visible light images that we can see, for example, from the Hubble telescope. So Hubble is a space telescope you can see just up here, observing in the optical range of the electromagnetic spectrum. There are also ground-based telescopes in the optical, like Keck's, probably one of the best ground-based telescopes. And of course, the telescopes that we might be more familiar with, you might be more familiar with for astrophotography or for observing. So the telescopes we have at Bayfordbury, for example, are for the most part optical telescopes that are observing that visible part of the spectrum. We can observe that very well from down here on the Earth. Of course, the atmosphere does get in the way and does, as Martin mentioned, cause the stars to twinkle as that light is distorted in our atmosphere. So for the very clearest images, we do need to go up into space. So that's why we have Hubble, for example, above our atmosphere, imaging the sky in much greater detail. But there are some parts of the electromagnetic spectrum that we can't see from here on the Earth because the atmosphere blocks them completely. So one of those is the X-ray. It's good for us that X-ray emission from space is blocked by the atmosphere. It'd be very damaging for our bodies, but it's bad for X-ray astronomy. If we want to take a picture of the high energy universe, we need to put our telescope in space. So the Chandra Space Telescope is one of the best X-ray observing facilities. And I've used Chandra data extensively in my research to look at the very highest energy processes in the universe. As we go down to lower energies, again, when we get down to the infrared submillimeter, we find a window where we can't observe from the Earth because the Earth's atmosphere absorbs and also produces a lot of infrared emission as it's warmed up. So again, we need to go into space. So Herschel is probably one of has the largest output of infrared telescopes. It's no longer an active telescope, but all of the data that it took over the years that it was active are still being used by astronomers to explore those lower energy processes. So I'll show some examples of the data that I have from different telescopes, a range of telescopes across the electromagnetic spectrum. So what do we see when we look at different objects in space with these different wavelengths of light? So here's a picture of the Andromeda Galaxy. So again, Martin mentioned, this is a very high resolution picture, of course, and we can see various colors of light, but this is all visible light that we would be able to see with our eyes if we could gather enough of it and create a good enough picture. So let's look at what it looks like across the electromagnetic spectrum in different wavelengths of light. So you can see we get a very different picture depending on the wavelength of light that we look at, because we're looking at very different energy scales of the physical processes that we can observe. So in the optical, we're seeing starlight. Move to the right side here. In the optical, we're seeing starlight, so the light that comes from stars. As we move down into the infrared, we're going to cooler processes. So we're seeing the warm dust, dust that is heated up by stars. As we go even further down to submillimeter, we see even cooler processes, so much lower energies. And if we get all the way down to the radio, we're not seeing thermal processes at all, but atomic processes from the gas. And if we go from the optical to higher energies, so we go up to the ultraviolet, we can see the very, very hottest stars in the Andromeda Galaxy. Into the X-ray, we start to see processes that are much more exotic still, the highest energy physical processes that we can observe, and then up into the gamma ray. I suppose gamma ray would be the very highest energy of those physical processes, and there we're seeing emission from the core of the Andromeda Galaxy. You'll notice that especially as we get to the gamma emission, it's very low resolution. It's just kind of one big fuzzy blob. So we can't see a lot of detail of what's going on there. And resolution will be something I come back to a bit later as well. So there's a lot we can learn about objects by looking at them in different wavelengths of light. And sometimes it can completely change our perception of those objects. So we realize an awful lot of information is lost if we only look at the visible light. So here I have a visible light image of a patch of sky. In the middle is an elliptical galaxy. There are hundreds of billions of galaxies that look very much like this one in the universe around us. They're pretty nondescript, these kind of fuzzy blobs containing hundreds of billions of stars. They're not quite as photogenic as galaxies like Andromeda or the Milky Way, which are spiral galaxies. But nevertheless, there are many, many of them in the universe. So if we look at this visible light image, we can just see an unassuming elliptical galaxy, and we wouldn't think much of it. However, if we look at that very same galaxy in the radio, we can see that something quite extraordinary is going on. There are these enormous radio jets that extend well beyond the extent of the galaxy that we can observe in visible light, so well beyond the stars in that galaxy, way out into the intergalactic medium. So we can see these jets which billow out at the end in the radio emission. And then if we look at the X-ray emission, we can see that there's some very high energy process going on around this galaxy as well, again, extending well beyond the extent that we can see in the visible light. So we can see suddenly that this galaxy is not like the other ones in the picture. There's something extraordinary going on. And what is it? Well, it comes down to supermassive black holes. So I'll talk a little bit about what a supermassive black hole is. I'm going to present this very much from my perspective as an observational astronomer. I'm not a theorist. I'm sure if you asked a theoretician what a black hole was, they'd give a very different answer. But from my perspective, a black hole is a very, very dense object in space. So the place where we usually find black holes is at the end of a giant star's lifetime. When the star runs out of fuel, that we have a supernova, the core of the star collapses as it becomes unstable. It collapses into an extremely dense object that becomes so dense that the gravitational field is so strong that even light cannot escape, which is why we call it a black hole. I often feel that black hole is a bit of a misnomer. It's not a hole in the sense that you could jump in it and go somewhere else through the hole. It's a hole in gravitational potential. So it's a very, very strong gravitational field around this very dense object. A supermassive black hole is a special case of black hole that we find in the universe, and we find them in the centers of galaxies. And they are many, many times larger than the kinds of black holes we observe at the end of a star's lifetime. So let's kind of get a sense of the scale of black holes. So in size scales, we have a supermassive black hole relative to the galaxy that hosts it. A supermassive black hole is a few light hours across. That means it takes light a few hours to travel from one side to the other. That's about the same size as our solar system. And relative to the galaxy that hosts it, which is 100,000 light years across, much, much bigger, that's equivalent to a grain of sand relative to the entire planet Earth. So we're thinking of something very spatially, very, very tiny compared to something very large, a grain of sand relative to the whole planet Earth. But if we look at the mass of that black hole, a black hole is about 1 billion times the mass of our sun, and a galaxy is about 1,000 billion times the mass of our sun. So now we're looking at an object with the mass of all of the Earth's oceans relative to the planet Earth. So if we had a black hole the size of a grain of sand, it would have the mass of all of the Earth's oceans condensed down into that tiny volume. So we start to see an object that's a little more unusual. And then if we look at the energy scales involved, a supermassive black hole has the potential to produce enough energy equivalent to 100 billion of the most powerful nuclear bombs on the Earth. That's enough energy to destroy the Earth 20 times over. So a single supermassive black hole at the center of a galaxy could potentially produce enough energy to destroy its own galaxy and then some. This doesn't happen, of course. If it did, we wouldn't see any galaxies out there in the universe. The way in which energy can be transferred and the amount of energy that's produced is limited. So we don't see supermassive black holes that are blowing the galaxies apart. Nonetheless, they do churn out a huge amount of energy into their galaxies, and that can have profound effects on galaxy evolution. So I'm going to come now to the questions that I have tried to answer. I've begun to try to answer in my PhD. So the first question is, do supermassive black holes stop star formation and halt a galaxy's growth? So we've seen a bit about supermassive black holes and the strange objects that they are and the huge amounts of energy that they can produce. I will pause a moment to actually explain how black holes produce that energy. So a black hole itself, as we said, light cannot escape from a black hole, so nothing can come out of a black hole. A black hole, once something goes in, it's there. It will never have enough energy to overcome the gravitational potential. However, as stuff falls into a black hole, it loses all of that gravitational potential energy. So we see, for example, in the picture above us, as that material falls in, due to turbulent and frictional processes, it burns incredibly brightly in a disk and it orbits the black hole in this very, very bright, what's called an accretion disk. And this process of losing gravitational potential energy as something falls into a black hole is the most efficient energy production mechanism in the universe. It's many times more efficient than the nuclear fusion that powers stars. So it makes these objects the most luminous things in the universe. It means we can see them to an incredibly great distance. and they stand out many times above the emission from the galaxies that they reside within. So back to our question, do supermassive black holes stop star formation? So we know that supermassive black holes in the centers of galaxies kind of switch on and off. Sometimes they're swallowing up matter and glowing extremely brightly, and sometimes they're quiet. So the supermassive black hole at the center of our galaxy is not active, it's not swallowing up material, it's not blowing energy out into the galaxy. The Milky Way is a relatively peaceful galaxy. However, there are lots of galaxies out there in the universe that are active with these active supermassive black holes. And this question, do supermassive black holes affect the galaxies they live in? Do they stop them from growing? Comes really from our understanding of galaxy growth and how we can test it in simulations. So astronomy is very much an observational science. We can't go out there and watch a black hole evolve and watch a galaxy evolve because these things take billions of years. But we can run a simulation on a computer to grow galaxies in a virtual universe and see if things work out the way we expect them to. So that requires putting all of the laws of physics as we understand them into a simulation, plugging in all the matter that we think should be there, and running the clock forwards. And so many of these simulations using supercomputers, incredibly powerful simulations, have been run to test our understanding of the laws of physics and the growth of structure in the universe. Now, when we look out into the universe around us, we can see the number of, we can count galaxies, we can see how big they are, we can see what color they are. And so if we just look at the size of galaxies and how many of them we observe, we come to this diagram here, which I'll try to explain very quickly. So on the x-axis on the bottom, we have the size of the galaxy. So we have small galaxies. Where are we? Small galaxies over here, and larger galaxies towards this direction. And then we can just see the number of galaxies on the y-axis from low to high. So we can see the blue dots on this diagram show the observational results. So if we just look out into the universe and count the galaxies of different sizes, these blue dots are what we would observe. So we can see there are lots and lots of very small galaxies. And as we go to larger and larger sizes, we have fewer and fewer of those galaxies that are very large. Now, if we run a simulation and we just put in the laws of physics and all of the stuff we see, and we run the clock forwards, and then we count the galaxies at the end, we find that many very massive galaxies are produced in much larger numbers than we observe in reality. So this dashed line that we can see here shows that result. And you can see at the bottom down here, my arms are disappearing, so you can't see, but if you look in the lower left of that diagram, you can see the dashed line is quite far away from the blue dots. It's marking that there are many more massive galaxies in the simulation than are observed in reality. Now, if we put, it's marked on this as AGN radio heating, and AGN is an active galactic nucleus. It's the name for a supermassive black hole when it's actively accreting matter from the galaxy and blowing energy out. If we switch on an AGN, an active galactic nucleus, and we switch on feedback from that supermassive black hole, that will affect the galaxy and stop star formation, either by heating up the gas or churning it up or blowing it out of the galaxy so that it can no longer condense to form stars. Then we see the simulation start to line up with reality. So we can see this non-dashed line is showing us that once we put that feedback on and stop the galaxies, we force the galaxies to stop forming stars by putting a black hole heating in there, we can match up our simulation to reality. And the simulation shows roughly the same number of galaxies of all different sizes as we actually observe in the universe. So that's great, we've solved the problem, but have we? Do we actually observe this happening? So I went out to look for observational evidence of this process happening, of supermassive black holes that are really active, stopping their galaxies from forming more stars. And the way I did that was using submillimeter light, which traces the very cold processes in the universe. So it traces the dust that we find where we have a lot of star formation. We produce a lot of cold dust that we can measure in the submillimeter. And then on the other hand, I looked at the X-rays for the very highest energy processes. So the supermassive black holes are incredibly high energy objects. We're seeing this X-ray emission from the accretion disk around an active supermassive black hole. So my hypothesis, here's an image which shows both of those kinds of emission in one image. So this is multiple wavelength images stacked on top of each other. We can see X-rays in blue and the submillimeter emission from dust in the red. So this is a galaxy that's very nearby. My galaxies are much, much further away and much less photogenic. But I thought this was a good example of combining these two different types of emission. So I do this using Chandra, the X-ray telescope I mentioned earlier. So this is a picture of Chandra. And here is a picture of the data we get from Chandra. So each of these bright blobs here is a point of X-ray emission, which signifies there's a supermassive black hole that is swallowing up material there. So this is a picture of the sky in the X-ray. And then on the other hand, for the submillimeter, I use a ground-based telescope called the James Clerk Maxwell telescope. It's on the top of Mauna Kea in Hawaii. You can see down in the lower left, there's a car. So just to give you a sense of the scale of this telescope, it's an enormous thing. And it collects the submillimeter light, which turns out to be very low resolution because we have very long wavelengths of millimeter. We end up with very low resolution images, even with such an enormous telescope. So this is a picture of the sky in the submillimeter, and you can see just about that kind of bright blob up there. That's a very bright galaxy in the submillimeter. It's got lots of dust. It's forming lots of stars. So just to give you a sense of the data I'm working with, they're not the beautiful, the stunning images that we see from kind of Stephen's photography. They're a lot of fuzzy blobs, but combining information on fuzzy blobs in lots of different wavelengths, we can understand about the physics that's going on. So this is my hypothesis. With a very, very powerful supermassive black hole accreting material and blowing energy out into its galaxy, we would expect it to shut down the star formation, to stop star formation from happening. So where we've got more X-ray power, which corresponds to more supermassive black hole activity, we would expect to see less star formation, so less submillimeter emission. So we measured the submillimeter and X-ray emission from lots of different galaxies, and this is what we were expecting to see, a downward trend like this. Where the lowest X-ray power had the highest submillimeter emission and the highest X-ray power had the lowest submillimeter emission. Did I say that right? You can see the trend on the graph. So we went away, we measured all our objects and we plotted them up, and this is what we got. And it looks a bit complicated, and I'll break it down into saying that there were lots of different types of galaxies in our sample at different distances where we're probing different kinds of physics. So we split them up into self-similar types of galaxies. We just split them by redshift, if you can see, so essentially the distance to the galaxy in the colors. So if I highlight 4 galaxies or 4 bins of galaxies of the same color, so these ones that are similar, we can see that the trend we get is not much of a trend. It's completely flat. So we don't see that downward trend that we're expecting. The most powerful supermassive black holes don't seem to have any different effect on the galaxies, on the star formation in the galaxies that host them, than the weakest black holes. So really, we didn't find what we were looking for. This is not a result that made any sense to us. And that's kind of exciting. Even though we didn't find what we were looking for, we did find that something's going on that we don't understand. The model that we're using in simulations that very cleanly explains how to produce galaxies of the right size is not backed up in the observations that we made. And there are lots of reasons for that, so I'm not going to go into them. But this is, I guess, the nature of research, that sometimes you don't come to a very satisfying conclusion. But potentially an interesting one with a lot of avenue for future research. I don't know how I'm doing for time, but I will very quickly go over 2 other questions, if that's okay, that I'm asking in my research. I'll go very briefly. In fact, you know what, I will skip this one because it is, I can come back to it if we have time. And then I will come to the 3rd question. Can we simulate the galaxies that are forming the most stars? So I already spoke about some drawbacks, some difficulties that simulations of the universe have. Another difficulty in simulations is producing galaxies that are forming enough stars. So we see galaxies when we look out to the very early universe that are producing thousands of stars every year. Our Milky Way galaxy is producing stars at a rate of about 1 star per year. So these galaxies are really furiously forming stars at a period of the universe's history that was extremely star forming. And simulations struggle to make galaxies that produce stars at those rates. So what I'm doing with some other researchers at the University of Hertfordshire is comparing simulations from a state-of-the-art suite of simulations that measures how galaxies grow across cosmic time, and comparing those to the best observations that we have taken with very high resolution telescopes of star-forming galaxies. And I'm trying to see whether the galaxies that this simulation spits out look like the galaxies we observe in the real universe. And that's very much still an ongoing project. I would say early results suggest, yes, we're doing a really good job. This simulation is trying some new things that other simulations haven't done before. And it's producing galaxies that are remarkably similar to the ones we see. So the picture that you can see behind me is a grid of simulated observations of these simulated galaxies, to see what would it look like if we were to look at these galaxies through a telescope of different quality. So we can see the very low resolution kind of fuzzy blobs over here up to much higher resolution. We can start to see the detail of where dust is in these galaxies, where star formation is happening. So that is my current ongoing project. This time comparing simulations and observations of reality. So thank you very much. I hope we have time for maybe a few questions just now, if anyone has anything they would like to ask. Jerry, shall I hand it over to you, or do you want me to look at the chat? Or
That's fine. I've got the chat up, so I'll go through some of the questions. But thank you. It's a very interesting presentation. I'm sure we'll all agree. So we have a number of questions on here. Let's start with, first a comment from Lewis Kelly. Wow, I wish I could see radio waves. So Tony has asked, if it's not a hole, how does matter fall into it?
I suppose one way of thinking about it is in terms of any gravitational body. So think about the let's think about the Earth. If maybe the Earth is a poor example. All right, let's go to the core of a star after it's collapsing. It's gone supernova. It's run out of energy. The core of the star is collapsing. The gravitational force that any particle around that core of the star is feeling, that gravitational force will pull everything down into a ball, right? And once that ball becomes a certain density, it will become a black hole. And anything else that comes close to it will fall and essentially kind of stick to the outside, I suppose is one way of thinking of it. And that would definitely upset a theoretician. That's very much a hand-wavy explanation of what's going on. Ultimately, we cannot see what happens to stuff that falls onto a black hole after it crosses the event horizon. So after that point where light can no longer return from it. So we don't know exactly where that matter goes, but ultimately, that matter is torn apart. It becomes not normal matter of atoms, but it's torn apart very much into its constituent particles. So it's hard to say where it goes. It doesn't disappear anywhere in that sense. It doesn't go into a hole and disappear. It just adds mass to the black hole. So as stuff falls onto a black hole, the black hole itself grows more massive. I hope that answers the question.
And that's how we get supermassive black holes, because they just keep more and more mass. I was asked this actually some while ago, and so I said, well, it's a hole in the sense that it's an area in space where you cannot see anything. So it's sort of visual hole in space.
I guess that's a good, yeah. I think of it in terms of a hole in gravitational potential. I remember from high school physics drawing kind of plots of gravitational potential, where you have a gravitational potential well. So like a ball will fall into it because then it gains gravitational potential, and it loses gravitational potential energy as it falls into a well. And a black hole, that well, gravitational well, will be infinitely deep. So it's a kind of a hole in that sense, if you're thinking in gravitational potential. But it's also, yeah, you're absolutely right. I mean, a black hole, it's black because we can't see anything. So it does appear kind of like a hole in our picture of space.
Okay. Alan has asked, if nothing can escape a black hole, what is in the jets? Well, they're not actually the hole itself, are they?
No, so they're not. So the jets and the accretion disk, anything that we can observe around an active galactic nucleus, it's not coming from inside the black hole itself. So nothing can come out of the black hole. But a black hole and its interaction with its environment can produce extremely strong magnetic fields. So as stuff falls into a black hole, it can get churned up and funneled out into radio jets. Again, a very hand-wavy description. I'm not a jet physics expert, so that was not a description of astrophysical jets, but essentially it's not material coming from inside the black hole itself, it's material falling in from around.
That's okay, that's fine. Jeff has asked, I assume the bright optical and X-ray sources also put out longer wavelength emissions as part of its spectrum. Does this cause problems?
Yes, I guess it does. So one of the very difficult things to do when you've got lots of observations of different wavelengths of light of, let's say, a galaxy, there are lots of different physical processes contributing to those measurements. So we have stars, which we know as a star has a spectrum, as you say, and that spectrum will have a tail that goes off into the lower wavelengths. For most objects, the amount of emission that they emit, the amount of radiation that they emit is constrained to a very small range of wavelengths where it makes a significant difference. So beyond a certain, when we go into the infrared, beyond a certain wavelength, we can say that the emission from a star is negligible when we're comparing it to everything else that's going on in that galaxy. But it is a real struggle. One of the things I've really struggled with is separating the emission from that dust from star formation, which peaks in the infrared and submillimeter, from the emission from the supermassive black hole accretion disk. So there's also a lot of dust surrounding that. Now that dust is a little bit hotter than the dust that we see around stars. So the idea is you can kind of separate them out when you look at the different kinds of emission, but it is a struggle because they overlap and contribute kind of in some places equally to the emission that we see from the whole object.
Okay, a couple more. From Duncan, ignoring the famous cosmic microwave background radiation, how come the visible universe isn't just an opaque fog of electromagnetic radiation?
Well, good question. I was actually just talking to a friend about this before. So I think what you've struck upon is called Olbers paradox. So the universe, I mean, as you say, the cosmic microwave background is exactly that. It's a dense fog of radiation. It just happens to be in the microwave regime, so we don't see it with our eyes. But with a microwave telescope, that's exactly what the universe looks like, a dense wall of opaque radiation in all directions, mostly the same. And the reason we don't see it in the visible light is because the universe has a finite age. So we can only see, let's get into this. So we can only see light that has had enough time to travel to us. So as we were looking at the images of Andromeda is 2.5 million light years away. So it takes 2.5 million years for the light from Andromeda to reach us. So we're seeing what it looked like 2.5 million years ago. As we look further out into the universe, we're seeing light that's taken even longer to reach us. The galaxies that I study, it's taken about 10 billion years for the light to less than that, 7 billion years. Let's go 7 billion years for the light to reach us. So we're looking back to when the universe was half the age that it is now. And as we look out further and further and further, we're seeing light from an earlier and earlier time in the universe's history. So eventually we hit that wall of the cosmic microwave background where we can't see beyond that because the universe was opaque. And it's the earliest emission that we're able to see. So if the universe were infinite, and sorry, not infinite, it were infinitely old, we would be able to see emission from stars across the entire sky. If it were infinitely old and static, let's say, just for simplicity, we'd be able to see bright starlight across the entire sky. But because the universe isn't infinitely old and that light is still traveling towards us, and we're also looking back in time effectively with that light we're seeing an earlier part of the universe's history, we see dark parts, I suppose, in our vision of the sky. I hope that made sense.
Oh, that's fine. That's fine. One last one then from Dan. He was asked, how long does it take for the simulations to run through 13.8 billion years of galaxy formation?
That's a good question. So one of the, I think it was the illustrious simulation I looked up the numbers for because I was very curious. And and it's 19 million CPU hours. So if you know about your computational power, you can estimate that. But on a normal laptop, it would take your laptop about 500 years to run that simulation. Fortunately, of course, we've got access to something slightly more powerful than a standard laptop. So the supercomputers that run these things are much more powerful, but it's still a matter of months to run one of these large simulations. So you can imagine if you find a bug in your code a few weeks after you've set it running, it would be incredibly frustrating. But there are a number of different simulations like this run on supercomputers, exploring different parts of parameter space, trying to understand different parts of our theories of how the universe works. And I will say they are very much simplified. We cannot possibly model every single particle interaction in the universe on a supercomputer. That's just prohibitively time consuming. So they all cut corners and they all make approximations, and that's where I find myself trying to probe those, say, well, is that assumption we've made, is that correct? By looking at the observations of the universe to see if those really match up.
Okay, well, we're going to hear more about that in May, because we actually had replies from 5 people, and the 5th one is going to talk about simulating galaxy formation. So you have that to look forward to in May. But for now, Jo, thank you very, very much for your presentation.
Thank you so much for having me.
So our next speaker is actually a member of the Society. John Collins is a mature student, although he claims that description refers to age rather than necessarily wisdom. His topic, well, the title is "The Hard Work, Processing Thousands of Automatically Taken Images and Encountering Various Snags and Catches." So there's an automatic camera that takes several hundred photos of the sky every day with various filters, viewing the same patch of sky. So he's going to talk about the challenges of extracting useful data from the results. And this is John's PhD project. So John, if you want to unmute yourself, and it's over to you.
Right, can everyone see that? Yeah, okay. Okay, I'm going to be talking about what I've been working on the past few months, and this is very much a work in progress, so I can't give you fascinating results as to what I've done, but I can show you exactly what I've been working with and the things I have to encounter along the way. I'm working with an observatory called the European Southern Observatory, which is in La Silla in Chile, which is the name meaning the saddle on the edge of the Atacama Desert. The whole site was inaugurated by the then president of Chile. It's got 3 main telescopes, large ones, and a number of smaller telescopes. And the one I've been working with is called REM telescope, which is one of the smaller ones. Just so you get an idea what the site looks like, this is an aerial view of the site, and I've got marked with a red arrow around about there is the actual telescope we're actually working with. It's nice and high up, so and the desert indicates there's rather little rainfall around there, which is a good idea. But there is a spot of cloud now and again, which causes confusion, as you'll see in a minute. Just so you know where we're talking about, we're in the southern hemisphere where most of the action is, where we're working with. You can see the location, it's sort of middle of Chile, just on the southern edge of the Atacama Desert. The actual telescope is called REM for Rapid Eye Mount, and it's automatically controlled. If you've just got the Dobson mount, it's basically one of those altitude azimuth mount, and it's all computer controlled. It's it's actually controlled, and the observations set up from a site in Italy, and this got staff members who just keep everything going, but they don't actually point the telescope anywhere. It's all controlled from over the internet. The rapid eye move, it allows you to move rapidly to a given patch of sky quite automatically and track things under computer control. I'm just going to go into a couple of schematics as to what it looks like. The light comes in on the left in this diagram, and it is divided in the green section into two parts. It goes straight through. It's got a what they call Sloan filter, which divides light, so that light less than a certain wavelength is reflected and light greater than a certain wavelength is transmitted. And the transmitted light is the infrared portion of the light from the stars, which goes into the larger red detector and then reflected down into the part highlighted in blue is the visible light. It actually contains a certain amount of the shorter wavelength infrared, as we'll see in a minute. Again, a further schematic is what's going on in the visible light part of the telescope. And you can see the light coming in on the left is split by one of these Sloan filters, it's called, into the longer wavelength here. It's reflected off the mirror, and then it goes into a further filter here for the two kinds of infrared, the shorter wavelength and the longer wavelength infrared. And then a similar process happens for the visible light, going to green and red parts of the spectrum. We don't bother with the higher wavelengths than that. We just are interested in the detection of the longer wavelength parts of the visible spectrum. When the light has been through these parts and been split into these four paths, we're mainly focusing on the optical spectrum. It's then focused onto a charge coupled device, which is 2048 by 248 individual detectors. This actually shows how it's projected onto the light is projected onto these detectors. This light, the color, I got color scheme over the years. It's been slightly adjusted one way or another to cover different parts of the area, just as the telescope's been reconfigured. So you can get the green part as the common area, but it doesn't really matter. The main point is that it's actually read as one unit and then subdivided into images for each of the four filters. So any given observation is exactly the same part of the sky taken with exactly the same exposure with the four different filters projected onto the slides. Now, the actual project is called the Red Dots Project, and they're particularly studying the very smallest types of star that is still a star, known as the M dwarfs or red dwarfs stars. And three in particular are being focused on the Proxima Centauri, which is the nearest star to the solar system, which is over 4 light years. And they've already detected 2 planets, one inhabitable, so one much further out, the size of about Neptune or so. The second one they're studying is Barnard star, which is the 4th nearest star to the solar system, and it's also had a planet detected around it. Barnard star is particularly notable in that it's the fastest moving star relative to the solar system. It's coming towards us at quite a rate, and it's also going across the field of view. It's called proper motion. So its position now is actually just in the northern hemisphere, but it's due to cross into the summer hemisphere if you're around in 10,000 years time. The third star we're looking at, again another M dwarf, is a bit bigger than the other two, is called Ross 154. It's quite a young star. It's got quite a speedy rotation period of just under 3 days, and because this stirs up quite a lot of activity, it's got quite a lot of star spots and flares and things that we like to study. There's no planets detected today. They get pretty well fried if there were any. Well, there's not time to talk about life and such on them, but it probably isn't. Why are we interested in M dwarf stars? They are the very smallest and coolest stars. As I said, anything smaller than that's not quite a star. It's called brown dwarf, and then you get to gas giant planets and so forth. There's a huge number of these red dwarf stars. There's 75% of the galaxy, and a bit more than that, in fact. And most other galaxies, by the look of them, consist of red dwarf stars, and 15 of the 20 nearest stars to the solar system are red dwarfs. So we need to get to know our neighbours a bit. It's also easier to detect motion of the stars due to planetary, because a planet goes around a star, not so much the star, but the common centre of gravity. And I'm sure you may recall seeing Jerry talk about Pluto, that nothing goes around the sun. They go around the common centre of gravity, which in case of Jupiter is outside the surface of the sun anyway. So because the star itself moves a bit, you can possibly pick that up, though not so much with this technique that we're doing at the moment. Another thing to note about red dwarf stars is they live an awful long time. Some of these bigger, brighter stars, they very much live fast and die young, and the very biggest stars, the O-class stars, only last a few million years, which is blink of an eye in cosmic terms, whereas the Proxima Centauri will still be going in 50 billion years time, long, 5 times after the sun has lasted, and 4 times as long as the galaxy has been going. Sorry, its universe has been going. Now, just looking at the observations, the REM telescope is shared with other projects, but you can see that the Red Dots project has hogged about 1/3 of the observations from it, and here is a list and a list of observations up to yesterday. There've been a few more today. I hadn't put those in, but you can see how many thousands of observations there are. And one of the things that must be obvious is we don't have time to really admire each individual picture. We need to be working on automatic ways of processing them and rejecting inappropriate ones and things obscured by clouds and what have you. This gives it's been going from mid-2017 to the present with a gap for reasons we all too painfully know about in the middle of last year. Okay, so what are we actually trying to do? What we want to do is we want to plot the light and how it changes over time. And we're particularly interested in periodic patterns. We're interested in periodic patterns because it helps us look for planets. As planets go around, as well as swinging the star around a bit, they also, if we're lucky, they'll pass right in front of the star and make a little dip in the light output. But when we're not looking for planets, we also like to study the structure of them. And like the sun, these stars have got spots and activity, and we can actually plot how much activity and what the motions of the spots, which tend to be fairly static over a given rotation period. And we can build up. Here's an example from a recent paper showing how we can get an estimate of what the distribution of spots are on the surface of the star. So with that, let's just have a quick look at some of the actual resulting images we get from the telescope. And here is a sample image. In fact, it's Proxima Centauri that I'm looking at, and this big blob here is actually Proxima Centauri. And these are basically raw images from the telescope, and you can see they look a bit sort of washy. Don't forget, this is really quite high. There isn't much different. We're trying to get as much as we can, but you can see that we've got a base level of 300 and odd, and a height of only 4,400. I'll come to what the count these numbers are in a minute. But the point is, it's not a great difference between the brightest and the darkest. And one thing I ought to mention is that we tend to produce images in negative format, so that the brightest things come out darkest on those display. It's just the eccentric things that astronomers tend to do. Now, if you're going to be just looking at snaps of your family or landscapes or whatever it might be, you don't really care that one pixel in your camera is slightly redder or bluer than its neighbor. But when you're trying to do accurate counts of what is the actual light output for stars, which is what we have to do to sort of measure these kind of fine variations, you can't put up with well, this is about right. You've got to actually calibrate each individual pixel individually. And this is where the hard work comes in. So the first thing we have to do is what we call apply a bias file to the each image, and bias each detector, the charge coupled detector, each pixel has a count from 0 to 655, and then depending on how much light falls on it, it'll give a higher or lower figure. It's an integral value, but it's never actually zero, because there's always a base level, even if you left the lens cap on. And you've got to, it's around 300, as you've probably seen from some of the previous diagrams. And so in order to get how much light has actually fallen on it, you've got to take that bias off. The problem is the bias changes for each pixel, and to some extent over time. And here is an example of one of the bias files used. You can see there's a structure here. The readout is by columns, and you can see that some columns have got higher bias values than the others. Not a lot. It's about 20 out of 300, but it's still a lot you've got to take into account. You can't just do an average value. The second thing you've got to do when you've taken that off is you've got to measure the sensitivity. The pixels aren't the same sensitivity, so the same amount of light falling on one might give a higher reading or a lower reading than its neighbor. So as well as the bias files, we have to do a file that gives a ratio to apply to each pixel to make it give the same value, the same light. And these are what are called flat files. Here's an example of a flat file that we use. It's hideously exaggerated compared to the images, but you can see that, you know, the images in the middle are much more sensitive than the ones on the edge. You are compromised a bit on the edge because of the sides of the camera, or sort of vignetting and various things in the obstructions in the way. So you tend to probably ignore the, you know, edges a bit. So when we've finished doing all that, what we got sort of before and after, and they probably don't look a lot different to you, but you can probably see how there's some of the shading, not all of it though, has been cleared up, and it's looking sort of more even around the edges. Now, actually constructing these flat files is a joy in itself. So, but I haven't time to go into that. So if we enlarge that right-hand picture, we get this. And I've also put in identified some of the objects. I've put Proxima with a pink blob, and I put some of the objects I've actually identified, other objects marked with yellow, and things I haven't yet identified, though I have identified that one in the past few days in green. And what we actually do is we count the number of pixels in this, for example, in Proxima, and all the surrounding objects. We try to take we try to select that one objects that aren't too variable, and group some alike from that, and then divide one by the others, because we can't, it's not really calibrated in terms of this count, it means this. You've got to compare the known, basically what we know are fairly stable things against Proxima itself, to get a table of figures for each of the observations of how much light we've got from Proxima or the other stars that we're interested in. And a nice little snagging a catch is that they're not all the objects are in all the frames. So it might, Proxima or Barnard star or whatever you're looking at might be top right in this frame, and then the bottom left in that frame, and different stars are surrounding, and that's just to add to the joy and fun. And so the task then is having got our flat files and our bias files. We need to, because we can't do all this by hand with thousands of observations, we need to develop tools to look at them automatically, say, I don't think this, I believe this observations is clouds and cosmic things hitting the detector and all kinds of things, giving various poor signal to noise. But having got through all that thing, we developed a table of intensities against time, and for individual observations, pull the filters together, pull close in time together, and various combinations of that. We compare what we've got with other projects, and then the main thing is looking at planets, rotation period, activity. Is it sort of constant? Does it come in cycles? Is it a regular cycle? Can we deduce things about spots? And then hopefully there'll be enough information if we've managed to pick our way through all the minefield of writing up and developing useful conclusions. I hope I've kept it reasonably within 15 minutes, and that's all I'd say.
I think Jerry is mute. So Jerry, would you like to take over?
Sorry, I lost the connection again. Sorry, that's the Wi-Fi here in a hotel. John, thank you for that. Duncan has asked, he said, I thought that everything, galaxies, etc., was moving away from everything else as the space expands. But you mentioned things moving across our field of view, not just away, and there's galaxies moving towards us too. How come? Well, basically it depends on the scale that we're looking at. But John, do you want to say more about that?
Well, yes, I think generally speaking, everything is moving away, but sort of in the local, the sort of galaxies are moving towards each other, but the stars are moving around within our galaxy and at varying speeds.
And Jeb has asked, do you have to detect and correct for transitory gain pixels, what I would call blinkers?
Well, basically, I haven't really had time to mention it. Some of the pixels have sort of periodic freakouts, and they suddenly do enormously high readings out of the blue, and then some of them just drop out completely out of the blue. There's not any in the particular CCD array I'm working with. There are none that are never responsive, but there are some that suddenly go and have a bit of a sulk one day and decide they're not going to do anything, and then the next day they're fine. But the neighbour will have a bit of a sulk the following day. You know, I mean, it's just adds. So you've got to sort of, you recognise this because when you subtract the bias, it goes negative, which causes all kinds of headaches. So you've got to spot the negative ones and work around it somehow. Guess at what the thing would have been if it from its neighbours, and try and guess at what it should be. But this.
Well, it isn't a guess; it's an estimate, John.
It is an estimate, I guess. Well, basically, you one of the things I didn't think I have time to mention is what they study, the point spread function, as it's called, of the actual source, so that you can actually you sort of look aside on picture of the profile of the image, and you look at that, and if where it's sort of dropped out a bit, you sort of say, well, the last time I looked at it, it looked sort of like that or like that, and so I think I'll draw in a bit just like that to fit in, if you see what I mean. But this is I didn't think there was enough to cram into. I've gone way over 15 minutes or something, but
okay. Don't worry about it. Thank you very much, John. And perhaps we'll get an update on the work at some point later on.
Yes, I hope so. I'll finish the PhD before I get the other foot in the grave. But
okay, thank you then. We now move on to Zhen Guo, who is doing a postdoctorate research as part of the Star Formation Group at the university. This is part of the world's largest infrared astronomy survey towards the galactic center. And he says that numerous variable young stars were discovered from the project and are discussed in his presentation, the new naughty newborns in infrared astronomy. So over to you, Jen.
Thank you. Thanks for this opportunity for us to share our work in Hertfordshire. So I'm Jen. I'm a postdoc in the Star Formation Group in Hertfordshire, and today I'm going to talk about the naughty newborns. And most of this work has been done in a big group called the VVV Survey Group, and the group member including people from Hertfordshire and from South America and across the Europe. So let's start. First of all, I think you all know lots about the atmospheric transparency, lots of the wavelengths of different radiations, and we can receive those from the ground. And today we're going to talk about a little bit next to the visible light. So the rainbow-ish color is the visible light. We can observe it from the ground, and the near infrared is right next to it. It's a small window, and you can observe lots of interesting things from this window. And also the good thing is we can observe them from ground base. We don't have to send satellites to the space, so we have enough observation time and enough facilities to observe those objects. So go into details. If we expand the near-infrared filters, we can see there are 5 filters in near-infrared, all designed to fit the atmospheric transmission. And you can see today we're going to focus on the reddest one. The one with the longest wavelength is called KS or K-band filter. And this one is beyond 2 micron to 2.5 micron. So let's go to next page. Oh, I think, wait a second, let's do it again. Okay, so this slide shows you why we want to use infrared astronomy to study stars or all the universe. So first of all, infrared can help us to detect cool emissions. For example, on the left, I show you a figure of myself in an infrared camera, and you can see my face here because myself also emit infrared light because I'm a cool object, not like a star with 1,000 kelvins. Well, this year, things changed a little bit. So this year, we actually use infrared cameras to detect people's temperature throughout all the airports around the world. And you can detect temperatures of the passengers here. And on around stars, there are also some infrared emission. And the very famous one is we can use infrared data to look at the disk around the young stars. And if you take a closer look, you can find some gaps and rings around those young stars. And those are opened by giant planets around it. It's quite cool. And in the bottom, you see, we call them black body emission spectra. So different temperature will emit different wavelengths of light. For example, around 6,000 Kelvin, which is around our sun's temperature, almost all the emission focus in the visible band. And with cooler and cooler, so cool stars around 3,000 Kelvin or even less than 3,000 Kelvin, those cool stars are actually only can be observed from infrared. It's quite cool. So if you want to observe those cool objects, you have to go to a longer wavelength, for example, infrared. And the second part here, so infrared observation can help us to detect the embedded object. As an example, I think all of you have observed, have seen the sunset and sunrise. You're going to see that when the sun is close to the ground, it's turned its color to a little bit red and orange instead of the yellow sun we see normally. So that is because you have very high atmospheric extinction in front of us when the sun close to the ground. And so the extinction itself actually will strongly affect the bluer light. The bluer the light is, you're going to have a higher extinction. So it will turn the object that looks redder. And we call this effect reddening effect. So this because we have cloud in our atmosphere. And we also have cloud in space. This is one of the dark cloud in space. If you observe it through visible light, blue, visible, and red bands, you can't really see things behind the cloud because it's all blocked or extincted. And however, if you use K-band, which is in the infrared, you can actually see through the cloud and see stars behind it because the infrared light is less affected by the extinction. So it's quite interesting if you want to see something behind the cloud, something behind an envelope of dust, and then you can use infrared telescope to see through it. So this is the very famous constellation we all know, Orion. And the Orion constellation is very interesting, not only because it's bright, it's huge, it's easy to identify. In astrophysicists' eyes, you're going to see, so here, you might see some little bit reddish blurry things around the star here. And those are actually star forming regions. And the cloud and young stars all over this region. So Orion is actually the closest and the largest star forming region in the galaxy. And if you look at them in the infrared wavelengths, you're going to see a whole different picture. This cloud structure was detected by IRAS. It's one of the first space-based telescope. And you can see some shiny cloud structures around the belt and the sword of the Orion. And also on top of the head, you see a cloud bubble here. It's all excited by the central hot star. Quite fascinating. And today we're going to talk about some individual objects. So we're going to zoom in to here. Here we have a very, very famous, maybe one of the most famous star cloud in the universe called the Horsehead Nebula in the Orion star forming region. It's a dark cloud, and behind the cloud, or within the cloud, there are thousands of stars forming at the moment. And we can see that we call them the womb of many stars. And the protostellar evolution was divided into 4 stages. Class 0, the star is still in the womb. And class 1 is actually a baby star. We call them a protostar. And then the star will evolve into teenager stage, class 2 and class 3. And then you can see around class 3 stars, they start to have planets around the star in the disk, and they open different gaps, quite fascinating structures. And eventually they will evolve into like solar system, like planetary system. And today we're going to focus on class 1 object. Yeah, focus on here, because there are many physics around it. So the class 1 star is surrounded by a huge envelope. And inside the envelope, it looks like that. So at the center is the young star itself, and around is a huge, massive disk formed by gas and dust. And then those material will constantly accreted onto the stellar surface. And due to the transportation of energy and also the angular momentum, the star gonna eject lots of outflows and jet and stellar wind. And on the left is the artist view of a protostar. It's not what we actually see. We can't have this resolution. And on the right-hand side is an infrared observation done by the VLT telescope in Chile. We call it a HH object. It's actually the jet launched by a young star in the center. You can't see the star itself, but you can see the jet here. Quite fascinating. And we're going to come back to this object later. So talking about the physics around those young stars, we focus on the mass accretion process on the young stars, because that shapes the protostellar evolution history. And on the left is the standard magnetospheric accretion scenario. I won't go much details on the scenario. You just need to know that the material is truncated around several stellar radii around the star, and then they follow the magnetic field line accreted onto the star. And the star is going to be really shiny because of this energy released by the material accreted here. And also the disk itself will have much emission. We're going to come back to this later. However, predicted by theoretical astronomers, the mass accretion process on young stars are not a steady event. It is an episodic event. So you basically see several accretion bursts throughout the stellar evolution history, and most of them are in the protostar stage or the baby star stage, which can only be observed from the infrared wavelengths. And this is what we want to observe, because throughout the history, even though the theory was published in 1996, we only have like several dozens of young stars have this very strong outburst. And we actually want to discover more objects with those bursting phenomenon on them. So what we're going to observe, we're going to use near infrared color to observe those stars, because you can't see them from optical. And we're going to targeting the galactic center because they have more stars around it. And we also want to extend our observation time from several days to several decades. We have a very long time interval, and then we can see those events. It's more like, observing a baby. So You go to another household, you see a baby, and baby always smiling to you, and you think, oh, the baby is so quiet, it's so nice. But actually, as a parent, if you with the baby 24/7, you know the baby gonna cry sometime. So that's what we are doing. So we're doing a very long-term monitoring to catch up those naughty young stars. So here is our telescope. The telescope we're using is a 4-meter telescope in Chile, and is so far the largest infrared survey telescope. But soon LST will be the next generation of the telescope. And our project here called VVV is the Vista Variables in the Via Lactea. This means the galactic center. And the co-PI of this project is Professor Phil Lucas in Hertfordshire, and we have a large group here. And also our science about the VV project, we actually want to identify as many as we can, identify variables toward the galactic center, and we want to study the length, the scale, the frequency of those prestellar outbursts. And the VV survey region really focusing on the galactic center region. You can see here, the blue region is our survey region, and all the other regions are different other projects done by the Vista telescope. So what we've seen here, I'll show you some numbers. I don't want to go to technical details. So this is what I'm doing now. So we select stars by looking at their variation amplitude. For example, if their K-band variation amplitude is 1 magnitude, if I change to linear scale, so the near infrared brightness change about 2.5 times, we can find 150,000 of stars in the galactic center have this kind of variation. And we can't really check each individual of them because there are too many. So if you raise the threshold for a little bit, you look at stars with delta K larger than 2 magnitude. Well, in the linear space, it's like 6.3 times, and you still find 3,000 of them. And even you go even larger, so you see, okay, let's select stars with brightness changes larger than 16 times, you see 300 sources. That's pretty much 10 times of previous discovered of all this kind of variables. So as an example shown in the bottom here is one of the most violent star we observed from this survey. And this star brightened by 8 magnitude in mid-infrared. If you translate into linear space, it's 16,000 times. The mid-infrared brightness of the star enhanced by 1,600 times. So this is not only a crying baby, this is a bursting baby. And what I am doing in Hertfordshire, we're trying to do spectroscopic follow-ups on those objects. We're going to identify the spectroscopic features of those stars. I don't want to really go into details, but basically, we can't really see the star itself because the light is blocked by the envelope. And we actually see is the cool or hot disk from the accretion disk. And also we're going to see light throughout the envelope and then see the molecular features, absorption from the water and the carbon oxygen moleculars. So, and we want to identify their accretion signatures or the mechanisms of their outburst. And on the right here is one of the example in infrared is the spectra. And we see features like here is the water absorption feature, and here is the CO absorption band here. So what about the mechanisms? How did those accretion bursts form? One of the theory is called disk fragmentation. So I have a small video here made by my colleague in Lancaster. So this is an accretion disk of a star. And you can see that with the time evolution here, the disk start to fragment into several small tiny disks. And that is one of the theory that they're forming giant planets around the star. However, theory predict that some of them will be accreted onto the star eventually, some part of the disk. And those accretion events can create those kind of giant outbursts and enhance the stellar brightness by 1,600 times. And another fun thing I've been working on is to study the outflow of those stars. We can actually use velocity maps. So we can see two components on the star. One is the stellar wind, low velocity component, and the high velocity component as the jet ejected by the star. By comparing 2 days data, so this one taken in 2015, April the 27th, and the right-hand side one is taken by 28th. Compare these two, you see, oh, shoot, the jet component just enhanced by a lot. If you take the difference between two velocity map, you see the jet component exists here, just in 1 day timescale. It's more like a hydrogen bullet ejected from the star, like this. And that's quite fascinating because people don't really expect the star can change the brightness of the outflow in timescale of 1 day. That's quite fascinating. And it's more like a laser baby. So, and in the last, I want to show you my ongoing work. We're actually selecting periodic accretion bursts. So those bursts may not only appear once, they might appear periodically. One of the scenarios is like there is a giant planet moving around the star, and the planet's gravitational influence of the planet will torque the accretion disk. So the mass accretion rate will be modulated by the Keplerian rotation of the planet. So this is our ongoing work. So currently I found 24 of them in the VV database. So here is my brief summary. First of all, infrared observation is crucial to study those embedded young stars. And the accretion bursts are very common among young stars, and the VV survey found thousands of them toward the galactic center. And on the left is one of the beautiful image we took from the VV image database. So it's a cloud. And on the right-hand side is our last group meeting in Hawaii. It's also my last academia meeting. So I'm really looking forward to have more like this year or next year. Okay, thank you. I'll stop here.
Thank you very much for that. When the slide came up showing the repeated sections during accretion, I was instantly thinking, well, what causes that? I mean, you expect accretion of material around stars to be constant. Well, perhaps not constant, but ongoing. And I was thinking, well, surely it doesn't stop and start again. But in fact, it's energy outbursts as a result of these accreted areas, as you say, coming into contact with the star. So essentially, would I be right in saying that what you're finding is not necessarily formed exoplanets, but you're finding the exoplanets being formed?
Yes, of course. So the current theory telling you that the exoplanet is actually, the planet is actually form around class 2 stage throughout the, the teenager stage of a star. But actually we can start to see that there are something happened around the baby stage. So we're trying to see that what actually we can observe. And if we see those kind of eruptive events, that means that there are ongoing planet formation even when the star was just born. It's a quite interesting theory to test.
Okay, well, thank you very much. And everyone else, do keep sending questions in, and we'll go through all of them after our last speaker. So we've heard from students. Now we're going to hear from one of the lecturers at the university. Carolyn Devereaux is a lecturer in astrophysics, and her research is on dark matter, the evidence and search for dark matter. And she says this can include some interesting stories about the astronomers involved in the discovery of dark matter. So over to you, Carolyn.
Okay, Thank you very much. I know it's getting late, so just to say it will be 15 minutes of talk, so it may not be many stories about astronomers on it, but there will be a little bit. So yeah, dark matter makes up about 85% of all matter in the universe. And that means only 15% of all matter is what we know and can see all around us and touch and understand. So most of the matter that exists is something that we do not know what it is. And no dark matter particle has been identified. So why do we think it exists and how are we looking for it? And this is what I'll talk about today. Right. So this diagram is a timeline of the story of the universe. Starts with the hot Big Bang, which expands space. As space expands, the universe cools. And it is this process of cooling that allows changes to happen so that the universe evolves and matter is created. As it cools further, matter is pulled together by gravity to form stars and planets and galaxies. Now, after the Big Bang, a lot happens, and within the first few minutes, particles are created and a soup of charged particles and light and dark matter exists. Now, dark matter is very important during this early time because it makes up most of the mass of the universe. It's what provides most of the gravitational pull for particles to come together and form stars. So without dark matter, there's not enough normal matter in the universe to create the gravity to pull particles together into stars, and we wouldn't be here. So at about 380,000 years after the Big Bang, the first atoms form. Now, light is not scattered by atoms, and so the light can now start to move in a straight line. Previously, it had been scattered about. So it can move in a straight line, and it moves through all the stars and galaxies over time until it reaches us today. Now, as it travels over time, it's stretched by the expanding space. So today we see it as microwave radiation. This light is called the cosmic microwave background. It was mentioned earlier, and it's all around us all of the time. So just to finish the picture, stars and galaxies sort of form about 400 million years after the Big Bang. Our Milky Way was formed about 4 billion years after the Big Bang. The solar system about 9 million after the Big Bang, and then the universe is roughly 14 billion years old. So today, that's where we are today. So dark matter played an important role in the early universe. And it also plays an important role in the universe today. And we can see that in the way galaxies rotate. And this is our first piece of evidence that exists for dark matter. So as long ago as 1933, the Bulgarian-Swiss astronomer Fritz Zwicky, which I always think is a wonderful name, was looking at the rotation of the Coma cluster. Now, the Coma cluster is a collection of about 1,000 galaxies held together by gravity. Now, Zwicky calculated how much mass was in the cluster when he looked at the amount of starlight. And from that, he could estimate the number of stars and therefore how much mass there should be. And this is the normal matter in the cluster, the stuff that we can see. He then calculated the mass by how much gravity there must be in order to hold the galaxies in the cluster. And he could work this out by measuring the speed that the galaxies in the cluster rotate. And that's very fast, by the way. They move about 1,000 kilometers per second. What he found surprised him. The two measurements of mass did not match up. The mass from the rotation was about 400 times bigger than the mass seen in the stars. So he concluded that there was missing matter, and he called this dark matter because he couldn't see it. Now, his observation of dark matter was correct, but his calculations were too big. Today, we calculate it to be about 5 or 6 times more than normal matter. So despite his evidence, the existence of dark matter was not accepted till nearly 50 years later. So why was this? Well, Zwicky was a character. He was an established scientist. had achievements in neutron stars, supernova, and he even developed the underwater jet. But he was a lone wolf and quite abrasive to his colleagues. He had wild ideas, like moving the whole solar system to a new habitable star. So he was not really listened to by the scientific community, and the concept of dark matter was just a little bit too wild to be accepted. So it took until 1978 when the American astronomer Vera Rubin studied the way 10 galaxies rotate using the latest high-resolution equipment. And like Zwicky, she found that much more matter needs to be in the galaxies than when we see it from the starlight. And I've shown here the type of rotation curve, as we call it, that Rubin was looking at. And what's interesting is so this is the center of the galaxy, this is the radius as you go out from the galaxy, and this is the speed of rotation. So as you go further out from the center, the rotation speed stays high. It is a flat curve, and it shouldn't be like this. If we use Newton's laws of gravity, it should get less, following this curve here. So in order to explain this, we need to add dark matter. And Rubin's rotation curves were sufficient evidence for people to accept that we needed to put dark matter into our model to our picture of the universe, our picture of the way galaxies rotate, to be able to explain what we see. So the second piece of evidence comes from gravitational lensing, from which we can produce a map of where dark matter is, and that's this map here. So gravitational lensing, very quickly, is shown in this diagram. We've got gravitational lensing is when light is deflected by the pull of gravity as it passes close to a very large mass, such as a galaxy, just like an optical lens focuses light. And the fact that light is bent by gravity was predicted by Einstein in his theory of general relativity in 1915. So the diagram shows light from galaxy 2 here being bent by galaxy 1. So at the Earth, we actually see galaxy 2 as 2 images. And this is this inset here shows an actual picture of a galaxy where we see 4 images of the galaxy sitting behind another galaxy. And there's this ring as well, which we call the Einstein ring, which is indication of gravitational lensing. Now, in the same way, the cosmic microwave background, which we talked about earlier, is also bent by the galaxies that it encounters on its way to Earth. And we can detect how much it is bent and work out where the matter is. And since most of the matter in the universe is dark matter, what we're seeing is a map of dark matter across the whole sky. And that's what this image is here. So this is the whole sky. And the blue areas are where there is a little bit more dark matter than average in the universe. And the yellow areas are where there is a little bit less dark matter than average. And these gray bits, the gray bit in the middle is actually the Milky Way, and the light from the stars of the Milky Way stop us from seeing the universe beyond it. So we blank it out. So this is a picture of 220,000 galaxies, about 200,000 galaxies. Each dot is a detected galaxy, and the closest galaxies to us are in the center, and then they get further away from us outside. So it dims off a bit because it's more difficult to see galaxies further away. Now, it shows that galaxies are not randomly spread throughout the universe, but they form a large-scale structure, which we call the cosmic web. And it looks like a gigantic 3-dimensional spider's web, and it consists of clusters of galaxies, filaments, voids where there are no galaxies, and walls of galaxies. And this is our third piece of evidence for dark matter. When we compare these observations of the cosmic web with computer simulations, we find that the pattern can be reproduced, but only if significant amounts of dark matter are added. And I'll show you now a video of a computer simulation. So this is a computer simulation created by the illustrious collaboration, which Joe mentioned earlier. It's a video of dark matter forming the cosmic web from the very early universe. So we're at about 1 billion years now, and through to today. You can see that the blue is the dark matter being pulled together to form clumps and filaments. And these slowly grow and become the large-scale structure of the universe. Now, as the dark matter clumps grow bigger, there becomes enough normal matter in the clumps for stars and galaxies to form, and that's these red areas. So that's galaxies forming within it. And eventually, you'll see the stars exploding as supernova as the stars die. And the green is gas. So gases along these filaments that connect the clusters of dark matter and galaxies. And you can now see big supernova happening now with the red bits. Okay, I'm going to move on because we've not got much time. And the final piece of evidence that I'll discuss today is also considered the most compelling. And it is from this image of the bullet cluster. These two galaxies have collided head on. Now, since a galaxy is made of stars, most of it is space. So they've passed through each other. And the pink cloudy region is an X-ray image that shows where the hot gas is. Now, for a galaxy cluster, there is more normal matter in the hot gas than in the stars. Now, the blue region shows where most of the mass is. And so that's the dark matter and the normal matter. And that's been detected using gravitational lensing. Now, you can see that the mass is in a different place than the hot gas. So what's happened is the dark matter hasn't interacted with anything and has passed straight through, whereas the gas, which does interact, it interacts with its, the two gases interact and slow down, and so it hasn't moved as far as the dark matter. So this is a picture of the dark matter separated from the normal matter, and it's very hard to explain this picture without the existence of dark matter. So we have all this evidence, and it's pretty strong evidence that dark matter exists, but we don't know what dark matter is. We do know some of the properties that it must have, though. Firstly, I have to say dark matter is not dark. It is transparent to light. We cannot see it directly because it does not scatter or interact with light other than by gravitational lensing. We also know that it interacts with normal matter through gravity, but that it doesn't interact through any other forces unless it is a very weak interaction. And it is this possibility of a very weak interaction with normal matter that we are using to hunt for a dark matter particle. But all of this means that it's very difficult to detect dark matter. And so far, we've not found anything that we think it is. So there are some candidates that we've ruled out. We've ruled out matter that we know exists, such as brown dwarfs, planets, black holes that don't give out light, and small neutrino particles. They're particles that we know exist, but they're too light to be dark matter. I don't have enough mass. But even when we add all of these things that we know about, if we add them all together, there's not enough of them to be dark matter. So we are looking for new particles, and there are various types of particles that we're looking for. There are heavy particles that are too heavy to have been created in existing particle accelerators. And these are called WIMPs, weakly interacting massive particles. And there are axions, which is a type of WISP, which are very weakly interacting sub-electron volt particles. And one of my favorite names, the anyons, and it's so named because it could be anything. So I will talk through three types of experiment that are looking for these particles. Very quickly, these three things. So this is the ice cube neutrino experiment, and it's looking for indirect detection of a dark matter particle. Now, the idea here is that a dark matter particle could hit another particle and break up into smaller particles, which we can detect. This annihilation is very rare, so will only happen when there is lots of matter and very high energies, such as in stars or galaxies. So IceCube is looking for a burst of very high energy particles that are created out there in space when a dark matter particle annihilates. These then interact with our atmosphere as it comes to Earth, creating a neutrino shower that we can detect. Now, IceCube uses a 1 kilometer cubed piece of ice in the South Pole as the detector for the neutrinos. So when the neutrinos hit the ice in the South Pole, it gives off light, which is picked up by strings of detectors that have been buried 1.5 to 2.5 kilometers deep in the ice. And this is a photo of the lab itself, where the computing is done. And the strings of light here are an artist's impression of a neutrino event happening in the ice. Now, we're also looking to detect dark matter particles directly. So direct detection looks for dark matter particles interacting with the nucleus of an atom here on Earth. Now, the experiment pictured here uses xenon atoms. And because the interaction is very rare, maybe only one a year or less, it's important to stop any noise from other particles interacting with the xenon. So the experiment is done deep underground where most particles won't get through the Earth. There is 1 ton of cooled liquid xenon placed about 1.5 kilometers underground. Now, about 6 months ago, there was great excitement scientifically when there was an excess rate of events that was observed in the xenon detector. Now, it was thought that this may be a dark matter particle, but the evidence turned out to not be strong enough. So a 10-ton xenon tank is being prepared to see if this is enough to detect a dark matter particle. And lastly, there are many experiments going on looking at creating a dark matter particle, and these are being done in particle accelerators, such as this one here at CERN in Switzerland. This is the ATLAS experiment in the Large Hadron Collider, and you can see the size of the experiment. There's a person here near the bottom. Now, the aim is to collide high energy protons together and look for missing energy. So when the protons collide, they create lots of different particles. And when you add up all the energy that you know should be there in those particles, if there's anything missing, that could be a dark matter particle because we haven't detected it. So the hunt for the dark matter particle is the hunt for missing energy. Now, there is a lot going on in this field, but that's a whole other talk, really. That's all. That's pretty much all I've got time for. This is a very brief introduction to dark matter. If you want to find out more, I have written a book on cosmology. It's for non-scientists and students. It covers dark matter, dark energy, the Big Bang, inflation, and multiverses, and other things. It tells you where we are today in our ideas on cosmology, and also some interesting stories about how those ideas were developed and the scientists involved. It's called Cosmological Clues, and it's available from main online booksellers. And I shall finish there. Right, I need to unshare. Let me do that. Okay, oh, there's a few things in the chat here. Hi, Jerry. Hello, Jerry.
It went again. That was really quite fascinating, and it really is a remarkable subject. Steve, can you bring all of the speakers up together on the screen?
I can unmute, but I
Yes, yeah, you can do that.
I think everyone can unmute themselves, actually, if they wish.
If the speakers, unmute yourself. So they had a comment earlier on from Duncan saying, this one is going to annoy me. I have a strange hatred for the idea of dark matter. Now, in fact, I started saying some while ago, I sort of questioned this. I mean, I can understand the reasoning behind it. And what I used to ask was, do we actually need dark matter, dark energy, or do we actually need a better understanding of gravity? This is what MOND, isn't it? The modified Newton dynamics. Would you like to say anything about that first, Carolyn?
Yeah, if I'd had more time, I would have spoken about it. Actually, so there's something called the Pilgrim's Law. Mildehai Pilgrim was an Israeli physicist who noticed that if you modify the Newton's law of gravity, so that instead of gravity being proportional to the acceleration, it's proportional to the acceleration squared, or the pull of it, then you get a really nice flat rotation curve. It explains what we see very well. And because it explains what we see very well, it is called a law. Unfortunately, applying it to other areas that aren't galaxies, so that it doesn't explain what happens in the early universe. So in cosmology, or in astronomy in general, there is this thing where, so what our explanation for how the early universe works really well with dark matter, but our explanation of today's universe with how galaxies rotate actually works better with modified gravity. So there is a dichotomy there. But it is generally accepted, I have to say, by most scientists that there is more evidence that dark matter is there, and modified gravity has yet to explain all the things that we see, and dark matter explains many more of the things we see, but not necessarily all either. So that's why we accept dark matter at the moment, because it explains more of what we see.
Right. I mean, would you say, is there anything along the lines of quantum physics, where you have laws that work for, you could say, the universe as a whole, but break down when you get to a very small scale?
Well, quantum physics, the laws work really well. Okay, so they're very, very accurate. And the difference is we don't have an understanding really of what is happening. So to be able to explain that is more tricky. But the maths and the explanation, the way it works is very, very accurate. I don't think dark matter's in that category. Our model of cosmology is a working model. There's bits that we know don't quite fit, and we're working on trying to fit that. And it could be the way to fit that is a totally radical new model, or it could be that we just need more evidence and we need more observations. I think one of the exciting things about astronomy at the moment is there's a lot of these big telescopes that are coming out, they're coming online over the next sort of 5 to 10 years, and the amount of data we're going to get is huge. And some of these questions, well, it could throw up a whole range of new physics, or it could answer a lot of questions, but it may raise a lot of questions as well. But it's certainly going to be a very interesting time to be in astronomy.
Yes. Now, Duncan has followed up his observation by saying My mind is pretty full, so this question might burst it, but is it at all possible that the space the galaxies are in is rotating to provide some of the perceived speed?
Well, everything in space is moving with relative to each other. So yeah, so we're moving relative to, we're within the galaxy. If you look at us, we're within a galaxy moving, but we're also within a group of galaxies that's rotating around as well, which is also in perhaps so that you get to bigger and bigger areas, and that's where the large scale structure comes in, and we are influenced by movements of gas, for example, that go along these massive filaments that connect clusters together. So it's all interconnected, really.
Okay, there's a number of comments. I haven't seen any other questions, but we do have quite a number of messages from people. Oh, here's something from Paul. Is it naughty to suggest that astronomical theory is in a state equivalent to a modern version of Ptolemy, saving appearances, but with better maths?
I don't think that was naughty at all. I think that's very true. We actually consider it to be cosmology in crisis is a term that we use. And actually, so a science in crisis is something that is defined by as where we have more anomalies than more anomalies are coming, are being created than being solved, and we're sort of almost in that state with cosmology. We keep the more information we get, it's not quite fitting. We heard that today in what Jo told us, that it doesn't quite, she thought she was going to get one thing and got something totally different, which does happen in science. But there is this this state of being in crisis within cosmology where it could be that we might just need to change our whole model totally, but we haven't got another model to change it to at the moment. So we're sticking with the old one, and it could be that the old one is right as well, that as we get more evidence, hopefully those questions will be answered. But I think your analogy with Ptolemy is correct, actually.
Well, except to say that the advancements we've made in the last 100 years, the development of CERN, when you look back the thousands of years to Ptolemy, I mean, the advances that have been made in science in not even 100 years, in 50 years in cosmology is just incredible. I mean, give it another 500 or 5,000 years, and we'll have the answers.
Yeah.
Maybe even another 20 years, who knows? Because it is changing so rapidly. Yeah.
That's right. Exactly.
Yeah. Well, there was a fantastic program by Nigel Calder, back in the 60s, called The Violent Universe. If some of the other viewers who are as old as me might remember that. It just showed a complete revolution in astronomy, and certainly, I mean, not that long ago, when I was giving astronomical talks, and I said that really we have a completely new view of even the solar system and the universe to what the textbooks all said when I was a youngster. They said, oh yes, right, well, we have this, and so we've got a sun and 9 planets, and they all go around in the galaxies and that, and we found that there's so much more to it than that. But you mentioned about finding anomalies, and I'm reminded of a statement by the great science and science fiction writer Isaac Asimov, who said that the greatest leaps forward in science are not heralded by eureka, but by, oh, that's funny, when you find something unexpected and different.
Yeah, that's exactly right. Yeah, and actually, that's when one of the reasons I wanted to just talk through the different experiments in part for dark matter is because it shows that they're trying to look for that new physics. That's something that, oh, that's something that's we haven't seen before or doesn't fit with the model that we've got. And it's interesting that the astroparticle physics has now become a discipline in its own right, and is a very active area. And as much work, goes on at CERN for hunting for dark matter as we look at for dark matter elsewhere as well. So there is a lot of effort being put into it.
They found the Higgs boson, so I mean, who knows what else they might do. Actually, when I actually met Peter Higgs at one point, and I told him that I had been saying for years that when the scientists at CERN do finally determine that they found the Higgs boson, that they should celebrate with a cocktail to be called the Large Hadron Collider. He likes that, which I was about. Yes, okay. Anyone? Does anyone else like to ask any final questions? And we have one more new message, which has been typical of some of the others that have come through. Thanks to all four presenters. Wonderful wide view of astronomy research. Thank you all very much. Thanks for an interesting evening. I'm a complete amateur, but found it fascinating. An excellent evening. 4 fascinating talks, all presented so lucidly, and super graphics. Thanks to all. And there's one here that says, thank you to all the speakers. My 10-year-old watched the first hour and really enjoyed it. I will show him the rest later in the week. So presumably he's had to go up to bed. And last one in from Tony. This has been a wonderful evening, and I'd like to express my sincere appreciation to all involved. Very skilled presenters. And then he's added, what about the God particle? Well,
you just mentioned it, yeah.
No, it's the Higgs boson, isn't it?
Yeah. So, well, what else can we say? Thank you ever so much for agreeing to come to do this. And although you won't hear us all, let's give a round of applause for our speakers tonight. Thank you very much indeed. Now I had a little note here. What else? Yes, Alan has pointed out that Phil Lucas did give a presentation to the Society some while ago, and suggests that perhaps we might get him back sometime. So
he's super busy these days because of the whole schooling thing, but yeah, I encourage him to come back.
Okay, well, let's see if we can arrange something then. Now, a lot of you will be aware that the population of Mars has grown slightly. The United Arab Emirates craft Hope entered orbit yesterday, which was a terrific achievement for them. And earlier today, the Chinese craft also successfully entered orbit around Mars. The American craft, Perseverance rover, is due to touch down on the 18th of February. And some of you will have guessed this, but when it does, then I will as well, because my name is on the spacecraft. But this time I also registered my granddaughter, Phoebe, who will be 12 in May. So she's probably the only person in her school whose name is going to be on Mars this year. Now, on the subject of the exploration of Mars, I'm going to hand back to Alan, who has some, well, some pretty exciting news for us. So again, thank you to all our speakers tonight. We've really, really enjoyed it, and we've learned a lot. It's been really something. Over to you, Alan.
Okay, thank you very much indeed, Jerry, there. I just want to wind up the meeting now. If you bear with me for a couple of minutes, I can assure you it will be well worth it. First of all, I'd like to reiterate the thanks to all of our speakers, the visiting speakers and Martin, everyone who's contributed to make this evening such a terrific one. I don't think we've ever had one, so many different aspects of astronomy, and we could have literally gone on for hours and hours. So thank you very much indeed. And also thanks to all the new visitors that we had this evening. We were very aware that we had a huge number of people come along for the first time, and we would be very happy indeed to see them come back to future meetings. This is the week of the Countryside Charity Star Count, where you can actually take part in a bit of science yourself by going outside on a clear night, wrapping up warm, and once your eyes have become dark adapted, start counting the stars that you can see within the constellation of Orion. Details about where to send your results, you can find them all on our website. You can click the buttons and send your results up. What they do is that they collate the results from all over the country to produce a map of where the best places to look for stars will be. Have a little look at that, and I hope that quite a few members of our group and their visitors will be able to take part. It's a good activity that you can do with children as well, especially as often children have slightly better eyesight than us more mature people. Our next meeting is on Wednesday, the 10th of March at 8 o'clock in the evening, where Jerry has used his influence and obtained the services of George Tahu. George is the program executive at NASA headquarters in Washington, DC, and is also serving as deputy director of NASA's Mars exploration program. Wow, having heard that those spacecraft have just arrived, what better talk could there be? Well, I look forward to seeing you all there 1 month's time. Do come along, bring your friends. It's going to be another great evening. So on behalf of the Hertford Astronomy Group, to everybody, thank you very much indeed for coming along, and we look forward to seeing you again. So good night, goodbye.
Good night.
All right.
Good night, and thanks to the organisers.
Thank you. I'm closing down